Household electricity is delivered in the form of alternating current. However, most electronic devices are powered from direct current. A power supply is used to convert the high voltage alternating current from the wall receptacle to a lower voltage direct current. The drop in voltage is accomplished by means of a step-down transformer. The process of converting AC to DC is called rectification. We have a simple circuit here called a half-wave rectifier. It's going to take the alternating current from our source and convert it to a DC current at our load, which is a 10-volt light bulb with a wattage rating of 1 watt. The AC is going to flow through this diode. If we go up to the semiconductors tab, the plain rectifier diode is the first diode on the list. And if we go into its properties, it's a 1183. It's the first one on the drop-down list for type. This source represents the alternating current coming out of the wall after it's been stepped down by a transformer. The wall current arrives in the form of a sine wave, and in North America it has a frequency of 60 Hertz. In other words, we get one alternation in 1/60th of a second, or 16.6 milliseconds. Our transformer has dropped the wall voltage down to a voltage of 10 volts peak. Let's try out our circuit with a transient simulation. I'll go in to set up the options. We have a source that's running at 60 cycles per second. Should be kind of hard to follow. So if we slow it down by a factor of 60, if we make our animation time unit 60 seconds, then one cycle should take about 1 second. So we'll run the simulation, 1,000, 2,000, 3,000. We can see that our bulb is flashing roughly once per second. Let's take a look at our circuit again in analysis mode. I'll turn off the simulation. We should note that there's a voltmeter at the output here called V load. That'll help us identify the output waveform in the analysis. So I'll go to analysis, I'll select transient. We know that we have a 60 Hertz input, so one cycle is 1/60th of a second, or 16.6 milliseconds. So 0 to 50 milliseconds should give me about 3 cycles of the output waveform. We'll select 0 initial values, and here's our output waveform. I'll bring up a legend, and we can see that the output, the load voltage, is in red. So as the input source starts to go positive, this side of the diode goes positive, the diode turns on, and we have current going to the load. And the current through the load follows the current coming from the source, and we have power and the bulb flashes. During the negative portion of the cycle, we have negative on this side of the diode. The diode is turned off or reverse biased. No current flows through the load, and we have a flat voltage across the output of the load. If we look at the peak voltage being delivered to the bulb, we can see that it's less than the peak voltage coming from the source. The reason for this is the voltage drop across the diode. If we want to get a better look at the voltage across the diode, we can drop the voltage of the source. So I'll go into sine wave, and we'll change this from 10 volts peak to 1 volt peak, and then we'll go back to analysis and run the transient analysis again. So we can see at the peak, the difference between the voltage at the load and the voltage from the source is about half a volt. We can also see that the diode doesn't start conducting right away. If we zoom in here, we can see that the voltage across the load is 0 in the beginning until the source voltage reaches a certain level. So I'll go and I'll grab a cursor here, and I'll click on the source voltage, and we'll move over to the point where we start getting some load voltage. So this is the knee voltage of the diode. So we need about 0.3 volts in order for the diode to begin conducting. Once it begins conducting, it doesn't burn up more than about 0.5 volts. So it's a typical diode behavior. It needs a certain amount of voltage to turn on, and then after that its voltage doesn't vary too much.